Hey guys, today we're going to be solving problem 2462, total cost to hire K workers. So the problem is pretty straightforward. We're going to be given an integer array cost where cost sub I is the cost of hiring the ith worker. We're also going to be given two integers K and candidates. We want to hire exactly K workers according to the following rules. Firstly, we run K sessions and hire exactly one worker in each session. And then in each session, the way we choose a worker is based on their cost. We always want to choose the worker with the lowest cost from either the first candidate's number of workers or the last candidate's number of workers. If two candidates have the same minimum cost, then we break the tie by choosing the one with the smallest index. Now, if there are fewer than candidates workers remaining on either the left or the right, we choose the worker with the lowest cost amongst them, and again, we break the tie with the smallest candidate. The last important thing to note is that a candidate or worker can only be chosen once. Once we choose a worker, we can't choose them again. And we want to return the total cost to hire exactly K workers. So if we go through a quick example here, we have a list of costs, a K of 3, meaning we want to hire 3 workers, and candidates of 4, meaning that the candidates can come from the 4 workers on the left or the 4 workers on the right. So all of these are going to be valid. All right, so how do we choose our first worker? Well, we want to choose the minimum cost worker, and that is going to be 2 here and 2 here. So we have a tie for the minimum. Now we know that when we have a tie, we choose the worker with the smaller index, and so that's going to be this worker. And so we choose this worker, which means we've now paid for this worker. We've paid a cost of 2, and we can no longer choose them again, and so we remove them from our pile. And our K is now 2 because we've chosen one worker. All right, on to the next iteration. So again, we know that we are allowed to choose between the 4 workers on the left and the 4 workers on the right. We didn't take any workers from the right, so these are going to remain the same. But we did take one worker from the left, and so we can now add a new worker to the left since this old worker no longer exists. So now there's 1, 2, 3, 4 workers on the left. All right, and once more, we take the minimum cost worker. In this case, that's going to be this 2 right here. We pay for them, and then we remove this 2 from consideration. All right, and then we repeat the process once more. There's still 4 workers on the left. We haven't changed that. And now there are only 3 workers on the right? Now, importantly, we can't move over and choose this 7, right? This 7 worker is already included in this 4 set of workers. So we don't want to double count them. And so we won't add any candidates from the right side at all. And indeed, this comes from this stipulation right here, which says if there are fewer than candidate workers remaining on one side, you choose the worker with the lowest cost amongst them. And so we take only these 3 candidates for the last iteration. And since we chose our second candidate, we now only have 1 candidate left to choose. And so the minimum value amongst all of these candidates is going to be 7, right? And so we pay for this candidate, we remove them from the running, and we don't need to run any more iterations since we've chosen all 3 of our candidates. We add up the values and we get a total of 11. All right, so how do we want to solve this problem algorithmically? Well, we know a couple of different things. Firstly, we know that we want to consider a bunch of candidates from the left and a bunch of candidates from the right. And we know we want to keep track of the minimum value amongst them. And so immediately your mind should go to a min heap, right? We want to keep track of the minimum amongst a set of values, and we can add to or remove from that set of values. Now we actually want 2 min heaps here, one to keep track of all the values on the left and one to keep track of all the values on the right. And so if we have a min heap of candidates' values on the left and a min heap of candidates' values on the right, then we can figure out what the minimum is amongst the values on the left and amongst the values on the right, remove the overall minimum from consideration, add that to our solution, and then if applicable, if possible, we want to add a new candidate to either the left or the right heap, depending on where we just removed a candidate from. So let's go ahead and try and write out some of the code for this. So first, I'll just go ahead and initialize n to be costs.size. And I also want to keep track of where I am at any given point, right? I want to keep track of which candidate is the next candidate to add to the left or to add from the right. So I'll keep track of that with L and R pointers. Now we also need to keep track of our solution. This is going to be a long, and so I'll just go ahead and define our solution as 0 to start with. And the last thing that we know that we need is going to be 2 min heaps, right? And so if we want to initialize a min heap, we can go ahead and do that pretty simply. This is going to be a min heap of integers, and because the initial priority queue is set up as a max heap, we need to override that and say that this will be a min heap. And so we need 2 of these, one for the left and another one for the right. All right, so we know that the way we want to start off, right, is we want to add candidates number of workers from the left and candidates number of workers from the right. And so the way that we can do that is we can say for int I in candidates.length. For int I in candidates, we want to add a new candidate to the left and add a new candidate to the right. So we say left.push cost sub L++, right? And this is just going to take the value that we have on the left, initially starting at 0, and then move it up 1 after we've added this candidate. And similarly, we want to say right.push cost sub R minus minus, and that's going to do the exact same thing in reverse. It's going to add right candidates and then move our pointer backwards. All right, and so now that we've added all of our candidates, we want to figure out what the minimum is and remove that candidate, right? And so we want to do this k number of times. So we can say while k minus minus is greater than 0, while we have more than k candidates left to choose, we want to choose them. And then eventually at the very end, we want to return our solution. Right, so how do we choose a candidate? Well, we can say, the easy choices, right? If one of these priority queues, if we don't have any candidates on the left or we don't have any candidates on the right, then we want to choose the candidate that does exist, right? So our base case here will sort of be if left.size is 0, or we can just say if left is empty or right is empty, then we want to choose the candidate from the priority queue that is not empty. And so we'll say the solution equals, well, if the left is empty, then we choose from the right. And if the left is not empty, then the right must be empty, so we choose from the left. And then we remove that candidate from consideration. So if we just chose from the right, then we want to remove from the right. And if we just chose from the left, then we want to remove from the left. Now, if both priority queues have candidates to offer, then we want to choose the minimum amongst them, right? So if the left top candidate is less than or equal to the right's top candidate, then we want to choose the left's top candidate. And the reason we want to choose if they're equal, right, is because if you have two candidates with the same minimum value, then you want to choose the one with the lower index. And the lower index is always going to be on the left, just by virtue of the way that we do indices. And so we say our solution equals the left top value. And then we want to remove that candidate from consideration. So we say left.pop. And finally, we want to add a new candidate to the left if we can, if we're allowed to, right? If there's no overlap between a candidate that we've already added, then we want to add a new candidate. And the way that we can check for that is by saying if L is less than or equal to R, if our left pointer is still less than or equal to our right pointer, then we can add a new candidate because we haven't infringed upon the right space yet. And so we can say if L is less than R, less than or equal to R, then we will say left.push a new candidate, and that new candidate is going to be at position L. So we push cost sub L++. Now we want to do the exact same thing on the right. We want to say if the right's candidate is the better one, if it's the lower cost one, then we want to add that candidate to our total cost. We want to remove that candidate from consideration. And then if it doesn't infringe upon the left space, then we want to add a new candidate. All right. Okay, so there's one last case that we need to consider, right? And that is going to be where this process infringes upon the left and right space, if this causes an overlap, right? We account for overlaps between L and R here, but it's possible if candidates is big enough, right? There could be a situation where we're double counting values in both L and R. And example 2, I think, is a pretty good example of this. So in example 2, if candidates.length is 3, then we add 1, 2, and 4 from the left, and then we add 1, 4, and 2 from the right. And see, we've double counted these values, and we don't want that to happen. So how do we fix for that? Well, we know that this only happens if costs.length, right? If the length of costs is less than or equal to 2 times the candidate length. If it is, then we're doing some double counting, and we don't want to do that. So we know that if n is less than or equal to candidates times 2, we're double counting if we do this, and so we don't want to do that. If we're not double counting, then we're still good to do that. So what happens if n is less than or equal to candidates times 2? Well, in this case, we can just add the entire list of workers to a priority queue, right? Because we know that every single one of them is going to be chosen, or not necessarily chosen, but every single one of them is going to be in consideration because the amount of workers that we can consider is greater than the amount of workers that we have. And so we can simply add every single one of these candidates to a single priority queue, and because the other priority queue will be empty, we will always just add the minimum cost worker. And so doing that is super simple. We can just say for every single worker, for every single cost in costs, we want to just say add this to the left. We want to add this value to the left. And that's it. We've covered every single possible case. And I think we can go ahead and run this thing. Passes all of these test cases. And yeah, there we go. This is the daily for June 26th, 2023. Yeah, thanks for watching.